The next application of Gauss law is for a volume charge. Here we are going to consider a volume charge as a uniformly charged sphere. So let us consider the entire sphere is uniformly charged and the charge density is given as rho b coulomb per meter cube. We consider here the radius of this spherical ball is A. We have to find the flux density for this uniformly charged sphere by applying Gauss law. And one more thing we should discuss here. This is uniformly charged sphere and hence inside the spherical volume, the electric field is going to be different from one point to another, and external to this spherical volume, the flux density is going to be different with respect to the radius. So we can categorize the estimation of flux density in two regions. One is inside this volume and the other is external to this volume. In either cases, the flux density is going to be directed radially outward. We'll consider the spherical system of coordinates with the flux density vector d in the direction of AR cap. We will estimate the flux density in two regions, one inside the sphere where radius of the Gaussian surface will be less than the volume charge density, the volume charge that is R less than A. And the second region is the Gaussian sphere or the radius R should be taken outside the sphere, that is R greater than or equal to A. Here, the closed Gaussian surface is in the form of sphere of radius R in both the regions, where in first case, the Gaussian sphere here indicated in blue color is for the region R less than A, that is inside the sphere. And for the second case, the closed Gaussian surface is in the form of a sphere of radius R greater than or equal to A, which is outside this spherical charge. Let us estimate the charge enclosed in both the cases. The charge enclosed here is a volume charge. We can estimate it as volume integration rho v dv. Since the volume is having uniform charge density, this rho v is constant. We can take it outside the volume integration, which gives rho v times volume integration dv, which is the volume of the sphere. Now, when we consider the first region where the closed Gaussian surface is considered at a radius of R, which is less than A, in this case, the entire charge contained in the sphere will not be covered in the closed Gaussian volume. In this closed Gaussian volume, the volume will be only till the radius R, which indicates the charge enclosed. So this volume should be taken as volume of radius R, where R is within the sphere. So the volume of a sphere of radius R is 4 by 3 pi R cube multiplied with rho b gives the total charge enclosed in the Gaussian surface of R less than A, where only till this radius R, the charge has to be taken for evaluation of Gauss law. For the second region, that is outside the sphere, if I consider the Gaussian surface outside the sphere of charge at a radius R greater than or equal to A, now we have to evaluate charge enclosed as the volume integration of rho v dv. Rho v is constant and the volume which is including the charge is only till the volume of the sphere which is charged. That is only till the radius A, the charges are present. From region A to the external Gaussian surface, there are no charges. So this region greater than A will not contribute for the charge. So only till A, only till the volume of radius A, the charges has to be taken for evaluating Gauss law. So volume here for the case 2 or the region 2 is 4 by 3 pi A cube, which encloses the charge of charge density rho v. So rho v times 4 by 3 pi A cube will be the charge enclosed for the region outside the sphere. So we have the estimation of charge enclosed for two regions For r less than a, it is rho v times 4 by 3 pi r cube. For the second region, r greater than or equal to a, the charge enclosed is rho v times 4 by 3 pi a cube. We have to evaluate the left-hand side. For that, we have to consider the Gaussian surface integration. Gaussian surface in both the cases is a sphere of radius r, where d is constant because the radius is constant on the surface of the sphere. The evaluation of double integral ds will give surface area of the sphere. We know surface area of the sphere is 4 pi r square. So the evaluation of d dot ds over the closed surface of sphere is ds times 4 pi r square. We have to equate this to the charge enclosed for two different regions to estimate the unknown d for two different regions. First, taking the region r less than a, we have to equate this left-hand side to the right-hand side. So we will get the equation for ds times 4 pi r square equal to rho v times 4 by 3 pi r cube, which gives d on the surface as rho v by 3 times r, and it is radially outward, giving the direction as ar cap. For the second region, r greater than or equal to a, we have to equate this left-hand side, ds times 4 pi r square to the charge enclosed in the region 2, which is rho v times 4 by 3 pi a cube, which gives d on the surface as rho v by 3 times a cube by r square, and also in the direction of ar cap. So altogether, we can write the flux density expressions for two regions, one r less than a, another r greater than or equal to a. We can show the representation of variation of flux density with respect to radius r graphically. For r0, the d vector, that is the flux density is 0. When r increases, the value of flux density increases linearly with the slope of rho v by 3. And at r equal to a, it reaches a maximum, that is rho v by 3 times a. Further beyond the radius a, when you look at the variation of flux density with respect to radius, it is inverse square proportionality. So the curve is an inverse square proportionality curve beyond a. So this is how we can graphically represent the variation of flux density with respect to the radius of the sphere from 0 to outside the sphere.